Example 6. P and Q are the points with parameters small p and small q on the parabola x equals to 2at, y is equals to at squared. So what this means is that P is going to be given by 2AP, comma AP squared, right? We're just essentially replacing T with P. And the point Q is going to be represented by 2AQ, comma AQ squared. In part 1, we want to find the equations of the tangents to the curve at P and Q and show that they intersect at R given by A brackets P plus Q, comma APQ. So if we're to get started, okay, I've done this a number of times already. If I consider the tangent at P, right, so the tangent at P given by 2AP, comma AP squared, we know that we obviously start this by differentiating, okay, parametrically for dy dx. So we said that dy dx is equals to dy dp over dx dp. So in other words, if I differentiate y with respect to p, we get 2ap. If I differentiate x with respect to p, we're going to get 2a, and the 2a's cancel out, giving us the gradient of the tangent as p. So once we've got the gradient of the tangent, okay, then we can say that the equation of the tangent itself, okay, is therefore given by y minus y1 is equals to the gradient times x minus x1, right? And if I expand this while looking at y minus ap squared is equals to px minus 2ap squared, and move the minus ap squared from the left to the right, and that's going to end up with y is equals to px minus ap squared. So that's going to give us the equation of the tangent at P. Now for the tangent at Q, right, Q is given by 2aq, comma aq squared. Now, if we just stop and think for a moment, if I want the equation of the tangent at Q, we start off by looking for dy dx, which is now not dy dp over dx dp, but rather it's going to be dy dq over dx dq. So then I'm just differentiating aq squared, which is going to give me 2aq, divided by dx dq, that's going to be 2a, so the gradient just becomes q. And then when I look for the equation of the tangent itself, I'm just going to get y minus aq squared is equals to q times x minus 2aq. And what we're supposed to realize here is that everything is exactly the same, except for the fact that P seems to have changed to Q. So when that happens, we don't need to write all the working out again. We can use a very powerful word, right? We can say similarly, okay, because the process is going to be exactly the same. And the only thing that changes is we've changed the P to a Q, right? So we can say similarly, the tangent at Q, right, is going to be given by y is equals to qx minus aq squared. So now that we've got this, if I want to solve for r, which is the intersection point between the two tangents, let's call this equation 1, let's call this equation 2. Solving 1 and 2 simultaneously, the easiest way out of this is to just equate, okay? So if we start a new slide, okay, part 1 continue, okay, let's say we are solving simultaneously, right? Solving simultaneously for r, then what we're doing is we're solving y equals to px minus ap squared simultaneously with y is equals to qx minus aq squared. And if I rearrange, we're looking at px minus qx is equals to ap squared minus aq squared. And we factorize, while looking at p minus q loss of x is equals to a, right? And I've got p squared minus q squared after I take out the a. And we should all know that p squared minus q squared is the difference of two squares. So we can then factorize this into p plus q times p minus q. Now, given that we've got the two tangents and p and q are not the same points, right? P does not equals to q. So we can cancel the p minus q away, right? And that leaves us with x is equals to a brackets p plus q. So if I want to find the y value, we'll just need to take this and we'll substitute this back into equation 1. So if we substitute this back into equation 1, y is equals to px minus ap squared. So p times x is now going to be p times a bracket p plus q minus ap squared. And if I expand the whole lot, we're looking at ap squared plus apq minus ap squared where the AP squared cancels out, and my y value is simply APQ. And that shows, therefore, that R, which is the intersection point of our two tangents, is given by A bracket P plus Q, comma, APQ. Right? And that's all we have for the coordinates of R. Okay, so that's what we got for part 1. Now moving on, part 2, we want to find the equations of the normals at P and Q and show that they intersect at the point U given by negative APQ, comma P plus Q, comma A bracket P squared plus Q squared plus PQ plus 2. Okay, so that's extremely long and quite nasty. But let's take this one step at a time, right? Let's get the equation of the normals out at P first, and we'll obviously find the equation of the normal at Q by generalizing, and then we're going to solve it simultaneously for the intersection point. Now take note that part 1, when we're deriving the equation of the tangent, we said that the gradient of the tangent at P is given by P. Now what this means for us is that P represents the gradient of the tangent. The tangent and the normal are perpendicular to each other, so that means that we can say that the gradient of the normal at P is given by negative 1 over P. So with this, now, if I come along, right, so part 2, I can start off by saying that, well, at the point P, given by 2AP, comma AP squared, the gradient of the normal is equals to negative 1 over P. And what that means is that the equation of the normal at P is therefore given by y minus y1 is equals to the gradient times x minus x1. I need to multiply P to both sides. So that's going to give me Py minus AP cubed is equals to negative x plus 2AP. And if I rearrange, I'm going to take the minus x on the right to the left and the minus AP cubed on the left to the right. And that's going to give us x plus p times y is equals to 2AP plus AP cubed. So with this, we can now generalize the equation of the normal at Q, because if I want to find the normal at Q, it's just that I'm replacing, because remember Q is given by 2AQ squared, and everything, right, the process remains exactly the same, except every single value of P that we see is now going to be replaced with a Q. That's the only difference. So therefore, we can deduce the equation of the normal at Q by saying similarly, okay, the normal at Q should be given by x plus q times y, right? I'm replacing the p with a q, is equals to 2aq plus aq cubed. Now what I want to do is solve these two equations simultaneously in order to find out where they intersect. So to start, I'm going to say, let's label this as equation 3 and this as equation 4, right? The best way of solving these two equations simultaneously is actually to use elimination. Because when I look at equation 3 and equation 4, on the left, you guys can see that I've got an x term. So if I subtract the two equations, the x is going to disappear, giving me something in terms of y. Right? For example, if I take equation 3 minus equation 4, x minus x cancels away, and then I've got py minus qy, okay? So I've got py minus qy is equals to 2ap, positive 2ap minus positive 2aq. So let's say that that's 2ap minus 2aq. Okay, I'll put a bracket around it because these two are going to be grouped together a little bit later. And then I've got positive ap cubed minus positive aq cubed. So that's going to be ap cubed minus aq cubed. And with this expression, if we now factorize, okay, we've got p minus q, loss of y on the left, is equals to, from the first bracket, if I take out a 2a, so I've got 2a outside of p minus q, plus, and then from the second bracket, if I factorize out the a, I've got p cubed minus q cubed. And we can see that we've got p cubed minus q cubed, which is a difference of two cubes here, which we can factorize further. Okay, so we factorize this further while looking at p minus q, loss of y, is equals to 2a brackets p minus q plus a. And then the difference of two cubes for the p cubed minus q cubed bracket is going to give us p minus q times p squared plus pq plus q squared. Now, p does not equal to q, Okay, so p minus q does not equal to 0, so I'm just going to cancel p minus q, right? So I'm going to divide both sides by p minus q and everything disappears. And what this leaves us is a very clean y is equals to 2a plus a bracket p squared plus pq plus q squared. And of course here I can use this opportunity to factorize a out. So that's going to be a outside of p squared plus pq plus q squared plus 2. Okay, so that is the y value of our intersection point. Now remember that the equation of the normal at p is given by x plus py is equal to 2ap plus ap cubed. So if I want to find the corresponding x value, I can just substitute it back into the equation of the normal at p. Right, of course, we can also substitute back into the equation of the normal at q. It doesn't make a difference. But my preference is usually to play with p. So if I substitute everything back into equation 3, we're now looking at x plus p times y, which is a bracket, p squared plus pq plus q squared plus 2 is equals to 2ap plus ap cubed. And what I'm going to do here is I'm going to expand the brackets because a lot of things cancel out. Okay, so ap times p squared, that's ap cubed, plus ap times pq, that's a p squared times q. ap times q squared is apq squared plus 2ap, right? Of course, this is equals to 2ap plus ap cubed on the right. And you guys can see, for example, that I've got a 2ap on both sides. And you guys should also be able to see that we've got an ap cubed on both sides. So they all cancel. So what's left is x plus ap squared q plus apq squared is equals to 0. In other words, x is simply equals to negative ap squared q minus apq squared. And if I factorize the negative apq out, right, we've got brackets p plus q left. So in other words, we can now conclude that u, which is the intersection point of the two normals, right, is therefore given by negative apq brackets p plus q comma a bracket p squared plus pq plus q squared plus 2, and that's what we have as the intersection point of the two normals. Now just take note that part 1 and part 2 of this question, where we're looking for the intersection point of the two tangents and the intersection point of the two normals, they are considered to be standard bookwork. So make sure you guys can actually show this. So lastly, coming up to the last part of the question, part 3, okay, now it tells us that if PQ is a focal chord, then we want to show that the interval RU is parallel to the axis of the parabola. So the biggest thing here is if we know that PQ is a focal chord, okay, the condition that we're going to get out of this is simply P times Q is equals to -1. So if I check this, if P times Q is equals to -1, that's obviously going to affect the coordinates for R, and it's also going to affect the coordinates for U because you guys can see that P times Q is everywhere. So first thing I'm going to do is I'm going to show that if PQ is a focal chord, that P times Q is equals to -1, right? I'm obviously not going to take anything for granted, nor am I going to just quote these results freely. That's not how it works. So coming back to do all the grind work, part 3. So if we know that P is given by 2AP, comma, AP squared, and Q is 2AQ, comma, AQ squared, if I start by looking for the equation of the chord PQ, okay, gradient of PQ is equals to AP squared minus AQ squared divided by 2AP minus 2AQ. And we can see from this expression that if I factorize the top after I take out the A, I've got P squared minus Q squared left, right? That's the difference of two squares, and we know that that's going to be equals to P plus Q times P minus Q over, and then in the bottom, the 2AP minus 2AQ is going to be 2A outside of P minus Q, and we know that the P minus Q's cancel out. The A's also cancel out, and what's left is half outside of P plus Q. Okay, this is a very familiar result because this is like the 10,000th time that we've done this. Okay, so with the gradient of the chord, we can now move along to find the equation of the chord. So chord PQ is naturally going to be given by y minus y1. So I can use either P or Q, doesn't really matter which. I'm going to use P, okay? So I've got y minus y1 is equals to the gradient times x minus x1, right? If I expand the whole lot, I'm looking at y minus AP squared is equals to half P plus Q lots of x minus half times 2 cancels away. So it's minus AP times P plus Q. So here, if I expand the AP bracket P plus Q for simplification purposes, we're looking at the equation y minus AP squared is equals to half lots of P plus Q times x minus AP squared minus APQ. And we can see that the minus AP squared exists on the left and the right, so we can cancel them out. And what that leaves us with is the equation half bracket P plus QX minus APQ. And this is the equation of the chord PQ. So now if we know that the chord PQ is a focal chord, okay, so if PQ is a focal chord, then what that means is that it passes through the focus. And the focus is going to be given by 0, A. So if my chord passes through 0, A, then that means that A must be equals to half outside of P plus Q times 0 minus A times P times Q. This part is just 0. Okay, so if negative APQ is equals to A, if I just divide both sides by negative A, then it's quite obvious that P times Q is therefore equals to negative 1. And this is the focal chord condition. Okay, so how does this help in showing that RU is parallel to the axis of the parabola? Well, if we think about it, right, R is given by A brackets P plus Q, comma, APQ, and U is given by negative A PQ brackets P plus Q, comma, A brackets P squared plus PQ plus Q squared plus 2. So now if I know that PQ is a focal chord and P times Q is equals to negative 1, then what that shows is that R is going to be equals to A brackets P plus Q, comma, A times negative 1, which is negative A. Okay, take note that this is actually another property of the parabola. Sometimes we will be required to prove this for exercises. Okay, and what this thing here is saying is that when PQ is a focal chord, okay, the tangents will always intersect on y is equals to negative A. The x value doesn't matter because the y value here is a constant. So what that shows is that the intersection point of two tangents, right, such that if P and Q is a focal chord, then they'll always intersect on the directrix. Okay, so this is what it's saying, but this is not relevant to the question, so I'll let you guys ponder upon that when you guys see it. Secondly, for the coordinates of U, you guys can see that if I replace every single P times Q with negative 1, negative A times negative 1 is going to be positive A. Okay, I've got the brackets P plus Q, and then the Y value here is just going to be A bracket P squared plus Q squared. This PQ is going to become minus 1, 2 minus 1, that's just going to be plus 1, and that's what we have for the coordinates of U. And what your attention should be drawn to right now is the fact that R and U have the same X value. So in other words, to conclude, right, if PQ is a focal chord, okay, that's how we're going to get the condition that P times Q is equals to negative 1, okay, i.e. P times Q is equals to negative 1, then the X value of R is the same as the X value of U. And if I have 2 points where the X values are exactly the same, right, that shows that RU is a vertical line, okay? And a vertical line is naturally parallel to the axis of this parabola because the axis of this parabola is the y-axis. Okay, so it's parallel to the axis of the parabola. Okay, so that's all we have for example 6. Quite lengthy, but this shows pretty much what a good question will do. Okay, it guides you through a couple of parts in order to get you to draw some conclusion at the very end. Okay, and there are different kinds of questions, okay, there are different properties, so make sure that you guys expose yourselves to a fair share of questions so that you guys can see how they can be tweaked to ask different things. Okay, and they're pretty much always exactly the same. Gets you to prove a couple of things, use coordinate geometry, make some deductions. Okay, fairly straightforward. So that being said, this concludes example 6.